Now see here, next topic is electric flux. So see here, electric flux over any area represents the number of electric field lines passing through this area. Suppose if you have taken any closed surface like this, and in this closed surface you take any here small area here, that is delta S. Normal, there is outward normal to this is taken is your area vector. So first we consider here area vector. So by convention, area vector has direction actually here outward normal to the surface or to the area. So we can also write here area vector, this delta S is equal to n cap delta S. If we are taking delta S tends to 0, so we can write here ds is equal to n cap ds. So if you have taken any surface like this or the closed surface, it is a small area element if you are taking, this is taken as area vector and its direction is here outward normal. So outward you have taken normal, that is ds. So electric flux through any surface is defined as actually dot product of electric field and area vector. So this is your electric flux, which is equal to number of electric field lines passing through this area. So see here, electric flux through any surface is defined as by this vector E dot vector ds. So we can write here E ds cos theta, where theta is the angle between area vector and electric field intensity. Suppose you have taken electric field intensity is like this and area vector is here, this ds is to this side and this angle is given here theta. Then this we can write flux through this area is here E ds cos theta. If you are taking theta is equal to 0 degree, it means electric field intensity is like this and area vector is also here. Then the flux can be written here, flux is equal to E ds, that is here maximum. So theta is equal to 0 here, that means angle between area vector and electric field is 0, then the flux through this is maximum, it means maximum number of lines passing through this area. So now this is flux is equal to vector E dot ds can be written E ds cos theta. So if you are taking theta is equal to 90 degree, that means electric field is to this direction and area vector is over here, then this angle is 90. Here you will be getting if theta is 90, so flux is equal to 0. It means no electric field lines are passing through this area here. So this is the electric field, electric flux is 0 and we have also seen when the electric flux is maximum. If you are taking theta is equal to 180 degree, then a cos 180 is minus 1 and electric flux will be here, that is minus E ds. Now after this different cases of the electric flux, also we can get the total electric flux through the any closed surface. Suppose you have got any closed surface and now if you want to calculate the total flux through the surface, so first thing is here you divide the closed surface into a small area and calculate the flux through these small area and then you add them up. So we can also write here the total flux through any closed surface is like this, integration of over the closed surface E dot ds. This here circle represent integration in a closed surface. Unit of electric flux also can be written. So we know it, electric flux is equal to E ds. So we can write here Newton per coulomb into meter square. This is the unit of electric field intensity and this is the unit of area. So we can write here the Newton meter square per coulomb. This is the unit of electric flux and electric flux is a scalar quantity, so it can be added algebraically.